You've heard it 1,000 times. What goes up must come down. Gravity. But is it true? Galileo was the first to investigate gravity 400 years ago. He dropped balls from a tower in Pisa, watched them fall, and invented physics. But today, we're going to chase gravity, literally. Let's take that falling ball and turn its motion sideways. What if instead of falling down, a steel ball travels horizontally, parallel to the ground? Can you outrun gravity? Kinematics, the science of motion, provides us with an equation that tells us how far an object will drop for each second. G is the acceleration of Earth's gravity, 32 feet per second squared. The distance covered by a falling body is then 1/2 times 32 multiplied by the elapsed time squared. Simplifying, that's just 16t squared. After 1 second, the ball has traveled 16 feet. How far can you run in 1 second? Well, the fastest human, Usain Bolt, can reach 28 miles per hour. That's 41 feet per second. So, assuming he has instantaneous acceleration, we're ahead by a lot after 1 second. That's great, but let's keep going. After 2 seconds, our star runner has gone another 41 feet, and gravity now has traveled a total of 64 feet. We're still winning. After 3 seconds, the fastest man alive is 123 feet from the starting line. But the steel ball is now at 144. Oh no! And a second later, it's 164 feet versus 256. So clearly gravity is faster than us humans. How about a race car? Surely that can outrun gravity. Formula One race car can reach 205 miles per hour. Let's use that. That's equivalent to 300 feet per second. So we sub in our racer at 4 times 300 feet. That's way out in front at 1,200 feet. Let the race continue. The car is winning early on, but gravity is no joke. It just keeps getting faster and faster. After 19 seconds, gravity pulls ahead, over a mile since the starting line. So, let's go bigger. Rocket big. Now let's really test this. Once we go fast enough, around 17,000 miles per hour, we don't fall back to Earth. We fall around it. We're in orbit. Gravity hasn't stopped. We just found a loophole. So already, what goes up must come down isn't quite right. And we don't have any engines on. But gravity hasn't let go. Because of our motion, we're exerting an equal force at this altitude that is exactly countering gravity. We could be up here for a long time. There is a little air up here, and eventually our orbit would decay and we would start to slow down and eventually crash back to Earth. Let's not do that. But what if you really want to outrun gravity, as in never come back? How does that work? We need a little bit more speed for that. To escape Earth's gravity entirely, you need enough speed to counter the full effects of Earth's gravitational force. Your kinetic energy needs to exceed the Earth's gravity potential energy. Kinetic energy is 1/2 mass of the ship times the velocity squared. The gravity potential energy is Newton's gravitational force equation times distance, in this case the radius of the Earth. That's the gravitational constant big G times the mass of the ship, mass of the Earth, and divided by the Earth's radius squared. Gmm over r squared. We can now simplify, canceling the 2 little m's and r top and bottom, love when that happens, and solve for v, which gives us this nifty final equation. Square root of 2gm over r, which works out to be 25,000 miles per hour, called the escape velocity. At that speed, gravity just fades away, and we're off exploring the universe. What goes up must come down? Nope, not anymore. What if you tried this on the moon? Gravity on the moon is only 1/6 of what we feel on Earth because the moon has much less mass. So, a race here would be much different. The Apollo astronauts, wearing those bulky spacesuits, could walk about 3 miles per hour, but they could leap much further. Leaping speed for an astronaut is about 12 miles an hour. This is definitely the preferred way to get around on the moon. 12 miles per hour is 18 feet per second. So, after the first second, our astronaut has jumped 18 feet. And gravity? Distance is 1/2 the acceleration of gravity on the moon, which is 1/6 of g, multiplied by time squared. This works out to 2.6 times t squared. So after 1 second, our steel ball advances just 2.6 feet. Ha! Let's keep going. Our astronaut is doing way better than Usain Bolt so far, but after 8 seconds, gravity still wins, even on the moon. And what about escape velocity? On the moon, it's just 3,000 miles per hour. Remember, it's 25,000 miles to escape Earth's gravity. A small rocket will do, just like the one we use to leave the moon. What about visiting Saturn? That's a different story. If we wanted to get a close-up look at those cool rings, leaving would be much harder. Escape velocity for Saturn is 80,000 miles per hour. That's over 3 times faster than what we need to leave Earth's orbit. But could we do it? One of our fastest rockets was the New Horizons mission with a launch speed of 36,000 miles per hour. That's a NASA probe that left Earth in 2006 to study Pluto and the Kuiper Belt, a region of icy bodies beyond Neptune. So escaping Saturn from a dead stop would be a problem, but we've traveled much faster. NASA's Parker Solar Probe is the fastest spacecraft ever built, reaching a top speed of 395,000 miles per hour in 2023. The mission is to study the sun's outer corona and solar wind. How did we do it? We used gravity as a slingshot. The solar probe's flight dipped in close to the sun multiple times to pick up speed on each orbit. It's very similar to grabbing a stationary pole while running to go faster. We're converting rotational acceleration to linear speed. Spacecrafts have used gravity in this way for decades to change direction and get a speed boost while using minimal fuel. In the 1970s, the 2 Voyager deep space probes flew by Jupiter and Saturn to get close-up pictures and a gravity boost to pick up speed on their way out of the solar system. The only 2 man-made objects that have made it to deep space, 15 billion miles away from Earth. 47 years later, they are still working and sending back data about the uncharted universe. What will they encounter? Maybe a black hole. Could you outrun gravity standing on the edge of a black hole? Forget it. Nothing escapes. Not rockets, not even light. Want to learn what happens to time in a black hole? Check out this video.